Hi, this video is to show you how to work on problem 1 on page 16 of our class notes about quality control. This problem is a problem about a quality manager that is measuring the capability of a process to fill large boxes of cereal. They design the process to fill out these boxes with 40 ounces of cereal. But sometimes they have more, sometimes they have less in each box of cereal. So we have a target here of 40 ounces. Okay, this is what we are targeting for. And we have a tolerance of plus 5 ounces or minus 5 ounces. So boxes can vary a little bit from 35 to 45, okay? Then we collect a sample, and the sample shows that process is filling boxes with an average of 41 ounces and not 40 as we are expecting, and with a standard deviation of 1 ounce. Okay, so here's the first problem. Calculate the capability, this capability ratio, and the CPK capability ratio for this process. So let me start with a Excel file here. So the first step is take notes about the specification. So the target is 40. The tolerance is 5. Okay, and then we have a sample with a mean, which is also could be our mu, of 41 and a standard deviation of 1. Okay, so this is data from the problem. That's the first step. Then to compute the capability ratios, we're going to use this formula here. So the first formula we're going to use is this. So I'm going to use this in Excel. This is the upper specification limit and lower specification limit. Okay, so let's go back to Excel and let's compute upper specification limit. Okay, in this case is equal to 40 plus my tolerance 45, and my lower specification limit is equal to my target minus my tolerance. So these are the upper and lower limits, okay, from this formula. Now I'm gonna subtract one from another and divide it by, so my CP is going to be equal, open parenthesis, 45 minus 35 divided by 6 multiplied by the standard deviation of 1, which is our sigma. Okay. So that's the formula, that's what we used, and we compute that. Let's take a look at the answer here is CP 1.67. So we found CP 1.67. Now we have to compute, if we go back here, we have to compute CPK. So let's compute CPK. So CPK will use our sample mean, or mu, okay, and our sample mu is equal to our sample mu, and then we're going to use now CPK. Use these two formulas, first this formula and then this formula. So it's upper specific limit minus mu, and then we do mu minus specification limit, and we divide both by 3 sigma. Okay, so upper specification limit minus mu is equal to upper specification limit minus mu, and then we have 3 sigma, or 3 standard deviation. Now let's do it above divided above, let's do it above by 3 sigma. Okay, so I'm going to divide this by 3 sigma. So it's going to be equal to this divided by open parentheses 3 multiplied by my standard deviation, which is my sigma. Okay, that's 1.33. I have to do the same thing for the lower specification limit. So let me do that here. So I have lower mu minus lower specification limit. Now it's the opposite to have a positive number, okay? First is upper specification limit minus mu, now is mu minus lower specification. So let's go. So it's 41 minus 35, then above by divided by 3 sigma. This divided by open parentheses 3 multiplied by my 1 sigma. Okay, so that's my this results 1 point. Take a look, 1.33, and this one too is this one. Okay, now this formula is telling me, this mean is telling me that I have to select the minimum of these two. What is the smaller of these two? So my CPK is going to be the minimum. This one is the minimum, so I'm going to select this one, equal 1.333. Okay, so this is how you select. Let's take a look at results. So these are the results matched to what we are doing. Okay, let's go back to the problem. What proportion of product from this process would you expect to be defective in the worst tail? Express this proportion in parts per million. Okay, so in this process we're going to let's go back to the problem. We know that the sample mean is 41 when it should be 40. Okay, so if I use here my Excel just to show you, so I have 40, I should be filling boxes with 40, but now I'm filling up with 41. So imagine that I have a normal distribution here. So the mean of this distribution should be here, but it's shifted to the right. Okay, so when it's shifted to the right, I have to, the worst tail is the one that has been shifted. This is what the problem is saying. The worst tail is the one that was moved from the center to the right. Okay, so I have to compute this upper tail here. So let's do this. My upper tail in this case is the upper specification limit. Okay, that's my upper tail. In this case is the worst tail too, because shifted to the right. So this I have on this slide. Compute CPK, use the formula, determine if the process is shifted to the right. If it's higher than the mean, it's shifted to the right. That's our case. The mean should be 40, is higher than the mean, so it's shifted to the right. If the process shifts to the right, you have to compute the z value associated with the upper specification limit, and that's the formula we're going to use. Okay, so USL, so I have to compute the z USL, the z value associated with the upper specification limit. So I'm going to compute that upper specification limit. I'm going to open parentheses 45 minus the mu. How much is the mu? It's 41, close parentheses, divided by how much was my standard deviation. My sigma is 1. So that's my z value associated with the upper specification limit. So you do that, you compute this z, and then the next step is if it is upper tail, okay, and not just because only it's upper tail, but because it's a positive number. This z is positive, And remember from your class on statistics, if it's positive, then it is to the right, and then you want to compute what is left after we define an area, okay, of upper specification limit, and then we're going to use this formula 1 minus norm dsd norm.s.dist. We're going to use this formula to compute the fraction of, so fraction that is defective, okay? The fraction that is defective is going to be equal 1 minus norm.s dist, and then I select this is the z. You type comma, and then you type 1 because you want this cumulative here, and that's the fraction that is defective. You see that you have a weird number with the letter E. This is a scientific number because it has too many zeros. So parts per million, ppm, parts per million. How to obtain the parts per million? You get this fraction and you multiply by 1 million. So 1 million is, so you have 31 parts defective per million. According to this process is having 31 defective parts per million. Okay, let's take a look at the results. Since the mean blah 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 blah, 31 parts per million. Okay, so we solve problem 2. Let's take a look at problem 3. Now the manager is notified that the process variability has increased 1.5. Now the process variability means the standard deviation, or the sigma, has increased 1.5. We have to calculate everything again, and what is the fraction that is defective, okay? So let's take a look here. So we go to C. Now the standard deviation is 1.5. So my CP, remember the CP formula, if you take a look at the CP formula is upper minus lower divided by 6 sigma. So it's equal to upper minus lower divided by, open parentheses, 6 times the standard deviation. Okay, that's the CP. The CPQ is USL minus mu. The mu hasn't changed, so we can simply copy here this difference. I'm not gonna compute again because I have to speed up because my time is gonna finish in 2 minutes. Okay, and then if I do above divided by 3 sigma, then this one is going to be equal to this number divided by, open parentheses, 3 multiplied by 1.5. That's the CPK, one of them. I have to compute the other one. The other one is here too, is the same difference. This is equal, let's just copy this one, and then let's do above divided by 3 sigma, which is equal to this divided by 3 times the 6 sigma here, 1.33. So now I have to choose the smaller of the two, the minimum. So the minimum is 0.88. Let's take a look at the answer. You see here, similar result, CP 1.11, CPK 0.88. I'm going to stop here because I'm gonna run out of time. Let me stop here and continue the second video, the second part. I'm going to start from here and compute the fraction that is defective and the part per million and finish this problem.